Hello, everyone, and welcome to FuzzCon Europe Automotive Edition 2022. My name is Juliana Rahana. I'm the manager of FuzzCon Europe, and I will be your host for this evening. Our speakers and I are excited to have you all with us to gain insights into all the latest developments in automotive security through industry test cases, best practices, and some live coding sessions. We started the automotive edition of the FuzzCon Europe series last year as a way to help connect security thought leaders and industry experts to exchange ideas and collaborate to make the automotive space safer and more secure for us all. For this year's lineup, we've got an impressive collection of speakers from Continental, NTU Singapore, Cariad, ZF, and Argus Cybersecurity. The talks will dive deep into the latest research, successful use cases, and different methodologies for fuzzing integration. First off, I'd like to share a bit about FuzzCon Europe for those of you who may not be in the know. FuzzCon Europe is an event series hosted by Code Intelligence. Code Intelligence is an automated software security platform that helps developers ship more secure code. It helps developers to protect themselves against unexpected edge cases and empowers them to fix bugs during development. If you would like to get a first look, the company also offers a free CLI tool that helps you to integrate and run fuzz tests into your project directly from your command line or your favorite IDE. If you'd like to learn more about this tool, you can check it out at fuzz.ci/CLI. You should find the link shown here on the screen, as well as in the comments section. All right, so before we get started, let's do a bit of housekeeping. All information about our speakers, today's program, and more can be found on our website at fuzzcon.eu, so you can plan your attendance accordingly and follow along. More than 500 people have already signed up for this year's conference from all over the world, so that's really exciting to see how much of a community that we've been able to build. We are currently live on our website at fuzzcon.eu, on LinkedIn, as well as on YouTube. But don't worry, we'll be keeping an eye out for questions wherever you're watching. So you just post them in the chat and we'll be able to see them. During the talks, please submit your questions at any time in the comment section and we'll collect them along the way and present them to our speakers for answering at the end of each talk. If you miss any information during the talks, don't worry, as all the talks will be recorded and you will be able to find them again on our website again at fuzzcon.eu. So I will introduce each speaker ahead of their talk. So please feel free to give them a little virtual round of applause and show them support as they appear on the screen. If you have any further questions or concerns during the conference, please feel free to reach out to our organizational team at info@fuzzcon.eu, and we'll get back to you as soon as possible. So let's get started.
So next try, hope it works now. Okay, so the title already announced is the historical vulnerabilities in the automotive space. My name is Andreas Walkelgartner. I work at Cariad as a security engineer. As said, I developed a infotainment system, so I eat my own dog food. And besides that, I'm also working on integrating security tests in our CI/CD pipeline, working on fuzzing machine learning. My information communication technology in 2010 from the University of Erlangen, then stayed at academia until 2017 and got my PhD in computer science. Then I switched to Audi Electronics Ventures in 2017. And since then, I'm working in the automotive industry area of security. So short disclaimer in the beginning, so I will present some vulnerabilities. They are all publicly known, so there's nothing secret in here. They're all fixed, and yeah, so this is about educational purpose, not to blame anyone, but just to learning from the past. And also it will be focused on the car side itself, and it will exclude like the key fob range extender stuff, because this is more a technological vulnerability and not so much a software vulnerability. with that said, so our goal is to learn from the past, that we don't repeat it today. So this is the goal. Or as Captain Hindsight would say, like, it's always easier to give advice after it happened. So so probably you should have written this 64 bytes into this 32 bytes buffer. Yeah. So just going straight to the list of the most dangerous software vulnerabilities, which is always released by Micro every year, and it changed a bit over the years, but still we see that the most dangerous software weakness is the out of bounds write. So this is still number one, has a very high score, and then still also follows some out of bounds reads. This is also, like we see on the right side, is how the memory safety problems, which only exist in languages like C and C++. But we also have some other weaknesses like command injection, and yeah. So, and these are some of the weaknesses. I will give some examples in known vulnerabilities from the past where these weaknesses appeared in the automotive space. And as this is an automotive security talk, we of course have to start with the GPAC, the most famous automotive hack ever. So it was in 2014. Charlie Miller, Chris Velasek, I think you all know the story. So they attacked a Jeep Cherokee over Wi-Fi, and they could just basically gain control over the whole car. They could inject CAN messages, they could brake, they could activate the wipers, and yeah, and basically drive the car off the road. And as a result, Ford had to recall 1.4 million cars. Sorry, Jeep Chrysler, they had to recall 1.4 million cars, and their stock went down. So it had some real impact on the company. And yeah, so what was the problem? The basic vulnerability itself was very boring. So even in the report, Miller and Velasek wrote like they wished it would be more spectacular. It was just 4 lines of Python, which they wrote. They connect to some inter-process communication bus, and then they could just write, yeah, please execute this command, and like netcat was installed. So in the end, it was just connect to service and start the shell. So this is very easy. And so, of course, they did more stuff. Then in the end, they connected over mobile wireless, like not only Wi-Fi, but also the mobile network. And they reflashed the firmware so they could inject arbitrary CAN messages and so on. But the initial access was done via Wi-Fi and like with these 4 lines of Python code. So what is the problem here? So the problem was that basically the debug ports or ports were open which shouldn't be open. Besides that, like there was no input validation of the execute command, and it was a operating system command injection, so they could just pass any command into this inter-process communication tool, and then they could execute what they want. And so also there was no access control who can access this dbus interface. So if you know the port, and you could connect, and then you can execute code. So these were the weaknesses which were present in this vulnerability, and how you could detect this. So like imagine this was implemented with a system in C. So this is a function call which just executes everything which you give to this function, and it will start a shell and then just use the string which was passed and execute everything in it. You could use like clang tidy, for example, and check for certain coding guidelines, and it will tell you, hey, you're using the system function, you should not use this system function because like it violates the coding standard CERT-C rule N33 something. And yeah, it also this works for like popen with this static analysis. You could also do some taint analysis, like for example, also in the Clang static analyzer has some taint analysis, which tells you like what are your information sources, for example, like reading from standard in or reading from a network, and then you pass this data through several calls into a sync-like system, and like the system sync, the connection between the sync and the source in such kind of functions, they shouldn't be like direct. So you shouldn't be possible for an attacker to control the input of a function-like system. And like this static analysis tool would give you then this nice visualization and show you like where from the input you leaked your command into your system function, and where the input was tainted and where the tainted input was then executed. Of course, you could also use like tools like CodeQL, which you can use like in GitHub Advanced Security. It also does some taint analysis for you. This is also some predefined checks in there. You could also do this manually, but out of the box, it will also warn you about when you use command injection for this, and it will also tell you you have a tainted input and you use it in a certain function which shouldn't execute tainted input. So this will give you also this result and tell you, okay, this is a critical issue, and it is this kind of CWE weakness which it violates. You could also, of course, use fuzzing. We are at FuzzCon, so how we could use a fuzzer to detect OS command injection. So imagine it was like built with Java. So sometimes in the infotainment systems, we use Java. So with Jazza, you could use like a custom hook, which uses the function where you execute your program, and it checks that the first parameter, for example, in this example is like process builder, and process builder should not be controllable, the first argument, by an attacker. And it will check if the first argument is this predefined keyword like Jazz. And if it is, then we abort and give this result that we found, that we found this vulnerability by fuzzing. We could also use this technique for C-based or C++ based fuzzing. So we can say we can mock or like link the libc library, write our own system function, and like which intercepts each call to system. And if this system call is made with a certain string in the beginning, then we can throw an assertion and terminate the program. Otherwise, we can call the real system function and pass forward the arguments. And we can also then build our fuzzer, start the fuzz, and we also will get a result that we have a deadly signal because our assertion failed. And if we then dig into the finding, it will give us the stack trace and tell us where our assertion failed. And with this kind of thing, you could basically fuzz all C functions in libc. Of course, there you have to do some manual effort. Like for Jazza, there are already some predefined sanitizers for this kind of injections, because in Java, you don't have all the memory issues, so they have other bug finding sanitizers to find this kind of bugs, while in C and C++, the main focus is on memory weaknesses and undefined behavior. So they're out of the box. You use normally the memory stuff, but you could also write your own intercept and then assert on certain strings. So let's go on to a more current attack. It was like from 2020 when Ralph Philipp Weinmann and Benedikt Schmotzle from ComSecuris, like they attacked the Tesla Model 3, and they could open the doors and like without any click could control the car. So how did they attack the Model 3? They used Wi-Fi. And to make the attack more shiny, they used a drone. So they mounted some evaluation board on the drone, and then could like trigger this zero-click vulnerability from the drone. Their entry ECU was the infotainment, and the vulnerability was inside a connection manager called Conman. So this is formerly developed by Intel, then open sourced, and I think was then a Debian package. And yeah, so they could control door lights, unlock the car with a zero-click. So this was very nice. And how did they find this vulnerability? So they used fuzzing also. They used the AFL fuzzer. They took a look at the source code. They saw that it was all like pure C, mem copy all around, and the code like looks like crappy code. So they fuzzed it, and like within no time, they found a crash in the DNS proxy. Then they did further research, and they were able to exploit with two vulnerabilities. So like one was this stack overflow where they had a partial write inside the system, and the other one was an out of bounds read where they could then leak some addresses to circumvent the ASLR mitigation. So in the end, they had like these two kind of memory weaknesses found, and in addition also they used some kernel bugs in the Linux kernel to get the full access and full remote code execution inside the car. And if you see like the fixes here, like basically you have to add some more checks that in your mem copy you don't have an out of bounds write, or in the other case you have more checks that you don't have an out of bounds read. So this is common problems with C, that often you forget some checks, and with fuzzing it's easier, or you can detect such cases where you forgot your checking. Then 2 years later, like David Berat and Moussa Dehor from Synactive again tried to hack a Tesla Model 3. Again, they used Wi-Fi infotainment, and they used the same network manager. So the vulnerabilities in the network manager, they even named their vulnerability like T-Bone 2.0. So the original hack was like T-Bone, and now we have T-Bone 2.0. And again, they could control the car without any interaction from the user. So it was also zero-click attack. And yeah, so this time, again, we have two CVEs they found. It was like one was an heap buffer overflow where they could swap one byte, like from OA to 0, and the other one was a double free. So this two components, a bit different subcomponents of the con manager. So this time it was not the DNS, but like the Whisper is a hotspot detection module, and GWeb is like it's an implementation of HTTP GET POST queries. So with these two bugs, they could also gain a remote code execution. In addition, also they found like some Linux kernel bugs to get the full exploit chain, and like they spent 1 year of research on this. So this is not trivial to exploit, but in the end, again, we have two memory safety issues in the same module again. So let's take a look at the CVEs issued for the conman. So we saw until 2020, so before the first Tesla hack of this kind, like there was not much big security vulnerabilities found in this module, and one could think, yeah, like very secure module. We couldn't find any CVEs there, we can use this. But then if someone started to dig into this module, then they found like in 2021, they found some bugs in there, and then later again in the same module, they found bugs again. So it's like, just before people didn't look at this module, and when you start to look, you will find bugs. So this is also gives you sometimes a false sense of security if there are no CVEs for a certain module. So maybe it has a lot of CVEs, but no one took a look at it. So One approach here is like from the Open Software Secure Foundation. They have something like called like scorecards. That's how they want to quantify the security of an open source project. So they have like 5 different categories, like code vulnerabilities. So is there any known vulnerability for this code? How is the maintenance? How is the testing, and so on? And then they build a score from 0 to 10, and then you could, from this score, you can determine how secure the development of this software component is. Unfortunately for Conman, you can't evaluate the score because this is not hosted on GitHub, and the scorecard only works for GitHub. But if you take a look at some of the criteria, for example, the continuous testing, so they write, do they have CI tests? Do they use fuzzing? Do they use like a static analysis tool? And if you take a look at the Git repository of Conman, like this is the these are the unit tests. So they have like 2 unit tests. Of course, they have some integration tests, but like the unit tests, they only have 2. And they were written by BMW. So probably Conman was not only used by Tesla, but also by other automotive vendors. And in the end, like we have like 2 unit test files, and we don't have any other more testing stuff in this, at least which you can find in this repository. There's no CI, there is no fuzzing, there is no sanitizers, and so on. And given that like a communication manager, so it has a huge attack surface, so it connects to wireless, and like everyone can connect to it. And given this attack surface, there should be a lot more testing, and also the whole industry should invest into these kinds of modules which have such a role inside your infotainment system, for example, because they provide the first entrance to your system. Yeah, so this was basically the 2 Tesla hacks based on this same software module Conman. And hopefully, we move on to some other communication managers. And the next hack is a CanFD hack. So this was presented this year at Black Hat Asia by Ariel Kadishevich and Shaki de la Rea from Argus. And so here they attacked, like before we had infotainment systems, now they attacked an instrument cluster. The difference is here that this is not like the other infotainment systems were running Linux. And here we have a system with a Renesas processor. So this is more embedded and has a different processor. It doesn't run a full-blown operating system. And so they were able to attack this directly over CAN. So they forged the CAN messages and to trigger a stack overflow in a CanFD receive. And then they could trigger the backlight of the instrument cluster. So here the vulnerability itself was straightforward. Here the challenge was more to craft like CAN messages to get a reverse shell over CAN. So this is the interesting part of this talk, how to get access to this ECU over a CAN and not, for example, the Wi-Fi in the other hacks. So how could you detect this problem? So as it's they said like there was a buffer with 32 bytes, and like CanFD messages can have up to 64 bytes of data. So it's a classic stack buffer overflow. You can detect this with fuzzing. So if they would have write a fuzzer, like I don't even know why they used like a 32-byte buffer, because like normally CanFD messages 64 bytes. This is a static size for the max size. It's defined in normally in your CAN stack. So I don't know. I can only guess why they didn't do it with a 32 byte. However, like if you would use fuzzing, you can detect such bugs pretty easily. And then to fix this kind of bugs is also much easier than to write an exploit for this kind of weaknesses. Also, there is a link, you can try this out online, and yeah, see how the fuzzer will crash. And yeah, what you can also normally do is like, if you can't switch to Rust, so of course the classic mitigation for all memory safety problems is like, don't write it in a memory unsafe language, so switch everything to Rust. However, this is of course not feasible in every case, and yeah, it will take time to switch to Rust for some parts. But there's still some mitigations you can use, like in C. So you can still compile, given your compiler supports this with some mitigations. So fortify source. You can use this in libc, and also Clang supports this. And I think also like in muscle libc, there's some ways to use fortify source. So this will give you some bounce checking and makes it much harder to exploit and buffer overflow. Also, if you look back to the first stack smash for fun and profit, I think was from 1996. If you would execute this on a modern machine with all mitigations enabled, like it wouldn't work like this. So there has been a lot be done in this space. So if their mitigations are on, then it's much harder for an attacker to exploit this kind of weaknesses. We also saw this in the OpenSSL and the recent OpenSSL bug, which was downgraded later because like it was very hard to exploit. Yeah, so this was the state of the art which we are living in. And so what are the, how we can tackle this? So memory safety is still a huge issue, not only in the embedded device, so also like Microsoft, Google, Chrome, they all have still a lot of portion of memory safety bugs. And OSS Fuzz also still finds a lot of bugs which are memory safety. And yeah, so some trends, they are maybe shifting from like overflows to use after free bugs, for example, in the Chrome project, but still its problem is the memory safety, in the whole. And it seems like it won't go away overnight. Still we have fuzzing and everything, but still the problems are there. However, also there are some new mitigation proposals. For example, for the standard libc++ library in Clang LLVM, they propose that we use like hardening the buffer access in C++. So every time we access a vector or a span or something, and we access it out of bounds, that we don't have undefined behavior, but that the program crashes. So from a security standpoint, of course, this is much more desirable that your program crashes instead of like being an undefined behavior and being exploitable by a attacker. So if you maybe in some cases it can have some like performance impacts, but in the automotive space, like security is a much more concern than the performance. So in our case, like it would be nice to have this kind of hardening techniques that our like out of bounds access will then crash there. Another mitigation was proposed in the Chrome project. So they to tackle the use of the free bugs, they introduced a new kind of pointer, and it's called Miracle Pointer, and it does some ref counting. And after you, for example, free some memory, it will poison also this kind of memory area. And when you try to access, you will also get a crash or a bug, and you can detect this kind of use of the freeze, and it makes it harder for the attacker to use this use of the free weaknesses. And there's one other proposal to zero initialize objects on the stack. So basically, if you don't initialize your variables, this can also be exploited. And to use like zero initialization for all stack variables, the author claimed that it could have like eliminated 10% of all CVEs. And so Ruben Planet is also a Toyota company, so he's also working in the automotive space now, and will in our case, like there are also concerns about performance, but they also said like it has zero performance costs. Only in some cases where you have huge stack variables, there you can like opt out from this feature. So let's see how if this feature will go into the future C++ standards. Another thing is like C++ core guidelines. Like as an example, there are other guidelines, but these guidelines should prevent you to use like unsafe elements of the languages and like use like for example the TSL. They offer some bounds checked access to vector like to spans and so on, and like don't use naked new deletes, don't use malloc and so on. And with this kind of guidelines, it tries to prevent you from the bad corners of your language. Also, then there was a proposal from Herb Sutter. He's also working for Microsoft. He's in the C++ standard committee, like some new syntax CPP front, which you then compile from CPP front to C++, and like CPP front then basically uses these core guidelines and makes it impossible to use this kind of unsafe languages. It's very experimental, but let's see what comes out of this corner. There's something from Google, like Carbon. Also, there's some successor language to C++. Similar, you can then interopt with your C++ code, but have a better language to write new code. It's like Kotlin to Java, TypeScript to JavaScript, and so on. And also very alpha stage at the moment, but and see what we have in the future there. And so let me finish with some quote. So John Carmack from id Software, famously known programmer, they wrote everything in C back then, and he said like when he discovered some tooling to check for bugs, he tried out all the tools, and like even his code, he found a lot of errors using tools. So that just should show you that however, what a good programmer you are, you still will produce a lot of errors in C and C++. And it would be like, you should use all the tools you get your hands on and use these tools to make your code more secure. That leaves me with my summary. So I showed you some vulnerabilities in the automotive space from the past. Use this to learn from your future if you implement something similar, or use some third-party software which you want to use in your infotainment system or in another ECU. Like take a look at it. How is the software written? What could do there? Like could add some fuzz cases. Improve the software quality of this third-party software. Use something else. And if you know that you have some constructs with getting unsafe data or uses some pointer arithmetic on something like this, so this is very hard to do correctly. So there you should test enormously if you're using such kind of constructs. So contact me with my first name, second name at Carrier Technology, and let me conclude with fuzz over things now. Thank you.
Thank you so much, Andreas. That was really good. Let's see about the Q&A. So we're just going to give it a minute and see if we have any questions from the community. You can just post them in the chat. We'll be able to see them. Don't worry. Sometimes there's a bit of lag time, so let's see. All right, access to the slides, that one I can answer. We will send everyone access to the slides if you sign up via the website, and you should be able to download them as well afterwards if you haven't already signed up. So we have one comment, nice talk. Thank you, Alan. All right. Give it another minute or so. Yeah, some good feedback. Yeah. So you can see. Thank you, Philip. All right, so we've got the question there. Yeah, so you can see there, how would you, one second, it's moving so fast. How would you suggest one go about fuzzing third-party software, especially when you don't have access to the source code?
Yeah, so that's a good point. So of course, like the best thing would be have to have a source code access and then to fuzz the source code. If you don't have source code, you can still use some black box fuzzing, so which is slower, but you can still do some fuzzing there. Or you could write the person or like ask the people who deliver the software that they should do fuzz testing, so that to say like, in order that we buy the software from you, you have to do this and this testing, that you ensure us that you have written fuzz tests and you have like this and that coverage, so that they should prove somehow that they fuzz the code without showing the code. But of course, the best thing would to have source code and do it while during development.
Awesome. So we have a second question here from Marcus. He says, you talked a lot about programming languages, but some protocols like CAN are the problem because they were designed with security not in mind. Any thoughts on how to switch out legacy protocols in favor of newer and better ones?
Yeah, so that's a huge problem. So CAN was developed back then and didn't care about security. But the problem is that it's very cheap and yeah, it's just 2 wires CAN network and it's very easy. So it will still stay a bit because like as it is so cheap, so there are like some IP and automotive Ethernet. So there are newer protocols, but often they are more expensive. They need more like computational resources. And so, yeah, if you have new ECUs, like if you have more powerful ECUs, then you can go for a modern protocol, but some ECUs, I think, will still use CAN in the future, and it's will be hard to get rid of this kind of legacy protocols.
All right, perfect. Any more questions before we head on to the next talk? All right. Yes, thank you so much, Andreas, and your background. Everything was really insightful. If you want to contact Andreas, you showed your contact details as well. And you can also reach out to us at info@fuzzcon.eu if you have any further questions. All right, thank you so much.
Thank you. Bye-bye.
All right, so a little intro for our next speakers. There are Yukong Lee and Sheikh Mahbub Habib from Continental and NTU Singapore. Yukong is a research assistant professor in Continental NTU Corporate Lab, and his research interests include software testing techniques, especially fuzzing, as well as other security analysis and software quality assurance techniques. Dr. Sheikh is the head of growth field in security and privacy at Continental. He is responsible for leading and driving product, cybersecurity, and innovation activities within the Automotive Technologies Division. Their talk will propose 2 techniques for emulation-based fuzzing on IoT software and automotive fuzz driver generation. So everyone, if you could please give a warm welcome and a round of applause to our next speakers.
Hi,
Hi,
hi everybody.
can you see my screen now? Hi, everyone. Screen?
Not yet. Now it's coming.
Can you see my screen now?
Yes.
Stopped. Sorry, I try again. So you can see my screen now, right?
Yes.
Shall we start?
Yeah, we can start.
Okay.
Right. Okay, hello everybody. So I'll be starting the talk first, and then I'll hand over to you, Kang. Good evening, good morning, good afternoon, wherever you are. So we'll be talking about gray box fuzzing and how we bridge the gaps from the industry and academia perspective. Just short background on the collaboration. Continental started collaborating with NTU under Continental NTU Cop Lab from beginning of 2020. One of the work packages that we are looking into is how we can use fuzzing also for automotive and beyond automotive domains. And of course, we are looking at the white spots where we can generate innovations and also improve fuzzing activities, not only in automotive, but beyond automotive in other sectors like IoT, for example. Okay, why should we even care about software testing or software quality? It is a big issue. I mean, I'm not talking about only automotive, but in general, right? So I recently read an article which is called "Era of 9DZ Defects," which is of course not focusing on automotive, but there was a statement where the writer wrote about software bugs which can cost companies 100 million. And now we are actually following the era of software-defined vehicles, which means that 5 years back or 6 years back, when we were talking about 100 million lines of code, now in the era of software-defined vehicles, so we will be talking about 3 times more, 300, 400 million lines of code. And we might get more than 9DZ defects when we don't follow software security guidelines, not only in automotive, but in the IoT sector, where we are talking about millions of IoT devices connected to the one gateway and so on. So the thing is, such type of domain, when you have any vulnerability or security aspects, then such recalls will definitely cost you millions. And of course, you can see a kind of a trend in the technology domain. A lot of compliance or regulations are coming in, and projects that we are dealing with have to meet those compliance or regulations and standardization. Therefore, customers will come to you and we'll talk about complying with software security guidelines and standards. And a lot of OEM are coming, coming with the requirements that they indeed need fuzz testing for the new projects. And there you have seen what are the advantages that fuzz testing provides. And Andreas' talk from Cariad. And I think it was a very good talk to set the floor. And this will help everybody in this audience and also the other speakers to talk about it. Yeah, let's then focus on a little bit on the fuzzing part, a background of fuzzing. So basically, what is fuzzing? We already know from the previous talk. I don't want to explain more about it. It is actually about random inputs and testing the code's quality. In most cases, it is used for finding security vulnerabilities. Of course, it has a big advantage compared to static analysis techniques. It doesn't have such type of false alarms. Of course, if you don't prepare the inputs for the fuzzing in the right way, it could miss some bugs for sure. But it hardly provides you false alarms, which is the case in static analysis techniques. And it also has an advantage to generate what kind of inputs actually cause the crashes in or the bugs in the software, and this is a huge advantage that we have also seen some example in the previous talk. Now, when we are talking about fuzzing, there are actually 3 types of fuzzing that we know of. First one is the black box fuzzing, which is highly scalable because you just don't have to have access to the source code. You just do fuzzing on the compiled code, and it doesn't require program analysis in general. But of course, in this case, your input has to be well prepared. Otherwise, it will lack. So the based on the I would say non-effective inputs, your output can be also a garbage in this case. Therefore, white box fuzzing could be of benefit. It's highly effective because you can actually fuzz the source code, and also you can take inputs from the and mutate the source code in general, and then but it could be very slow because you will be fuzzing all specific lines of the code, and it also heavily depends on how you analyze the program. Of course, there are different techniques, symbolic code execution and such, which is highly effective, but it also not so scalable when we are thinking about 100 million lines of code or a full system fuzzing. Then it comes to a fuzzing. We don't have a fuzzing called black or white box, but we have another fuzzing that is called gray box. And gray box fuzzing is actually taking the advantage of black box and the white box, and those are quite scalable because you can actually set different pointers to the code, and at the same time it can give you feedback, and based on the feedback you can mutate the program in a way so that it will generate more code coverage at the end, and at the same time it will find more branches of the code and will find more defects in the code. So you can say it's a jack of all trades, but of course a master of none, because it definitely have some limitations, and those limitations we'll be focusing on today's talk. And with that, I will hand over to Yukang, where Yukang will talk about what are the different steps of gray box fuzzing is, and then he will highlight 2 of the contributions that we have made in the Continental NTU Corp Lab as part of our innovation activities.
Hi, thanks. Thank you, Sheikh. And I will introduce you the meta model of gray box testing or fuzzing first. So this meta model is very easy, and we use this model to think about what kind of problems we can solve and what kind of improvements we can have. So this model starts from and describes how gray box fuzzing works. So the first step is we need to generate a lot of test cases, and this is needed for any type of testing technique. And then, because testing technique is a dynamic technique, dynamic analysis technique, it requires us to execute the target program. So we need to feed the test cases to the target program and execute the target program with the test inputs. And after that, we can collect and analyze the execution feedback. But that's not all. We still need to use the feedback to adjust the test case generation. So you can see that we form a feedback loop, and we can continuously improve the generated test case according to the feedback of the execution. And the feedback part differentiates the color of box. So if we use more feedback from the program, then we are more towards the white box analysis, and the scalability may drop, but the effectiveness may increase. And If we use nice feedback, then we are more towards black box testing. Then the scalability can improve, but the effectiveness may drop. So here are some previous works in academia. So in academia, previous works are mainly focused on test case generation and execution feedback analysis. For example, for generating test cases, there are existing works for using some grammars or models to generate test cases, especially for JavaScript engines. And for collecting and analyzing execution feedback, researchers have come up with different ideas of collecting different types of feedbacks. By default, one of the most popular gray box fathers, AFL, is using only the code basic block or edge coverage as its feedback. But we can also use other types of feedback, such as the value of an interesting variable, or maybe the state of the program. So we can use different kind of execution feedbacks, and we can collect different kind of feedback. However, target program execution is kind of ignored in the research because it seems easier at first glance, and because we just execute the program. What's the difficulty here, right? So it's nice studied in academia. However, when we come to collaborate with our industry partners, we found that okay, there are actually two key challenges in practice. First, some targets need to be executed in emulated environment. For example, for IoT devices, for the firmware, we need they need some specific device to execute. However, it's not scalable because fuzzing, we want to have a high speed. We want to use some high-end devices or servers to run this fuzzing in parallel. But if we were to run them on actual devices, then it's not scalable. We have to buy a lot of devices, and the computational power of those IoT devices are not enough for us to speed up the fuzzing process. So we need to emulate some of the targets. So this is the first challenge. The second challenge is some targets do not even have a suitable executables because like fuzzing, we need to really execute the target. But some targets, such as the libraries, they don't really have executable suitable for fuzzing, or maybe there are some programs which involves a graphical user interface. Then it's not we cannot easily test those programs because we need to get rid of the graphical user interface to test the logic behind. So these are the two key challenges, and I will present you two of our works addressing each one of them. So the first work is emulation-based fuzzing. So just now I talked about a bit about the motivation from the industry perspective, because we have the software could be compiled for different CPU architectures, for example, for Intel, for ARM, or even for MIPS, and they may have different hardware dependencies. And most importantly, sometimes the source code may not be available. But from the academic perspective, we can see that, okay, there are existing works doing emulation-based fuzzing, but most of them are based on full system emulation. Full system emulation means that we are emulating the entire virtual PC, which includes the CPU, the disk, all the hardware, and the OS, of course. So the emulation speed is very slow. So the question here is, can we emulate IoT programs fully under user mode emulation? So this is our motivation from the academic perspective. So as you can see here, we are starting from a general problem, which is to do emulation-based fuzzing. And when we look into the academic perspective, when we really do some literature study, when we read some papers, we will come to some specific problems. So let me briefly introduce you our approach. And our approach is basically called observe and replay. The first step is we need to observe from full system emulation. We run the program on the test with a full system emulation once, and then what do we observe? We observe the dependencies of that program needed for user mode emulation. Such dependencies may include, but not limited to, launch variables, which includes basically environmental variables and dynamic files generated during the start of the process, and maybe some run config and some network behavior, because in this work we are dealing with firmwares running in routers, so, and maybe some other process resources, some inter-process interactions with other processes. So these are the needed sources. So the first step is we observe the full system emulation and then extract the needed dependencies of the target process. And after that, we have a mapping between the dependencies and how we should deal with it in user mode emulation. So we can resolve all the dependencies during the user mode emulation, and we can do fuzzing fully on the user mode emulation. And this can speed up the entire fuzzing process because we don't need to emulate the entire system. However, the drawback is we are not trying to find a perfect way of emulating any program under user mode emulation. We are only trying to do testing. So we are actually sacrificing some compatibility because we still cannot resolve some kind of dependencies when we transfer the program from full system emulation to user mode emulation. And however, we in exchange, we are gaining a lot of efficiency because the execution speed could greatly boost, as I will show you later. So now let's come to the evaluation of this work. From the experiments, we have found that okay, this we have tried on nearly 100 firmware images, and we found that in this with our technique, we can execute the fuzz. We can speed up the fuzzing by 26 times comparing with full system emulation. And from the real world point of view, we have found 10 vulnerabilities which can affect 18 different types of routers, and 6 of them are assigned with CVE IDs. So that's all about the first work, which is about emulation-based fuzzing. Now let's come to the second work, which is called automated fuzz driver or harness generation. So fuzz driver or harness refers to the same thing. So in case you don't know what it is, I will quickly give you a quick definition of what it is. So because there are because for libraries, for some programs, or especially libraries, there's no suitable executable program. In order to fuzz these library functions, we need to create a small program which can correctly invoke the library APIs in order to test it. So this small executable program is often called a fuzz driver or a fuzz harness. So the problem we observed from the industry practice is that programmers, they don't like to use fuzzing in real practice. They don't like to use fuzzing when they are developing their software, not because the current fuzzers are not strong enough to find bugs. It's not because of that. It's because they don't want to spare time to write fuzz drivers. Because in their point of view, writing fuzz driver is just an overhead. Because if I'm a developer, I will think that, okay, I've done enough of development. Why should I care about testing, right? So this is so writing fuzz driver is often an overhead for software developers, and it is important because most of the programs are not suitable for fuzzing by default. They need to somehow convert the program to a smaller executable which is suitable for fuzzing. So this is the problem here. And the second problem is even though some developers are willing to write the fuzz driver or fuzz harness, they don't know how to do it effectively because they don't have security background, they don't have testing background. So, or maybe they are not familiar with the project. They need to learn a lot to learn how to use the API functions correctly. So this is the second problem hindering the testing or applying fuzzing in industry practice. So from the academic point of view, there are existing works on how to generate fuzz harness or fuzz drivers automatically. However, they have some drawbacks. The biggest drawback is that existing techniques doesn't try to cannot handle control flow very well. By control flow, I mean it's like if, else, and loops. They are not handling this kind of program features very well. So this is the biggest issue. And as you can see, again, we are starting from a general problem, and when we look into the academic point of view, we are coming to more specific problems. So our basic idea of this harness generation is that we have a target library, and we have a set of consumer programs using this library, and then these consumer programs may not be a suitable target for fuzzing, of course. So what we can do is we can learn how to invoke the library functions correctly from the consumer programs. And what we are learning here is an automaton which can represent the correct usage of the API functions, because library APIs may have dependencies. They may have different control flow or data flow dependencies, and maybe we need to invoke the API functions in a correct order in order to test it properly. So this automaton can describe this the dependencies between library functions. And after that, we just convert this automaton into fuzz drivers, into the small programs needed for fuzzing. So this is our approach, and we have done some experiments on Java projects, and we can see that we can have improved coverage and bug detection compared with manually written harnesses. And for real-world impact, we have reported 151 bugs on 9 Java projects and received 3 CVEs. So just now I introduced 2 of our works, and in fact, following the big model of testing, we have developed a set of techniques which are all published as research papers in academia. So you can see, we can use this model actually to tackle new problems. I saw there are some people asking about protocol security or protocol fuzzing in the previous talk, and actually we can also use this model to think about how we can have improvements for protocol fuzzing, because it's also a very hot topic in academia. So for example, we can think about, from the input generation point of view, we can think about, okay, how can we generate valid packets communicated between the different parties of the protocol, right? So if the protocol is not open source, how can we learn the packet structure from the traffic, maybe? So that's one point of one improvement maybe we can do. And the second potential improvement is that maybe for executing protocol programs, we can increase the execution efficiency, because we don't want to start a server every time for testing, right? We may want to start the server from a state, and then how can we do snapshot of the server? How can we fuzz it in a persistent mode? Is a problem, and actually there are existing papers published discussing these topics. And of course, feedback collection, because most of the protocol bugs may not result in a crash. We may need to somehow observe we may need to introduce some other ways to observe bugs. And as for the feedback for guiding the fuzzing process, using the basic block level or edge level coverage feedback is often not enough to really drive the entire fuzzing process, to really drive the protocol from one state to another. So we may need to think about how can we use program state to guide the entire fuzzing process. And that's all about how that's all about the tool works and how we can use the meta model of fuzzing to think about new problems or new improvements we can do. So now let's come to the conclusion, and Sheikh will give you this conclusion.
Okay, all right. So you can hear me, right? So
Yeah.
yeah, so the last slide, what Yukang presented, kinds of draws me into the conclusion that yes, of course, there are a lot of fancy approaches and nice tools around, but we should always rather think about real world industrial problems around on the fuzzing or dynamic analysis part, and then we think about what are the research approaches out there. Are they fulfilling my needs? And then we come back to real world application. We try to implement them as we have also implemented a fuzzing prototype system in Continental together with NTU, and we kind of use our these innovations that what Yukang has presented, integrated into such solution and try some real world applications and try to enhance them because unless you are testing them, verifying them, validating them on the real world problems, you don't know how they are performing. So real world pilots and use cases are the key if you really want to generate some effective solution in the dynamic analysis while you're using fuzzing. So that concludes our talk, and we'll be ready to answer your questions, and also nice to have your comments as well. Thank you.
Thank you so much, Sheikh and Yukang. Let's see, we already have a first question here in the comments from Asim. He asks, which is the recommended approach? Emulation-based seems time-consuming approach versus the harness driver.
Oh, actually, they are not. It's not one or the other. The relation is not like this. So we can use both of them actually. For example, emulation is about how is about how can we run this program, but harness or driver generation is like what program to test. So this is they are kind of orthogonal to each other. So that's why we can there's no such more recommended approach. Yeah.
Perfect. Our second question is from Sanjesh. He asks, how is fuzzing different from TTCN-free conformance testing?
Conformance testing. Actually, fuzzing is more of a general topic. It includes almost the definition of fuzzing is related, pretty much related to its name. It's called fuzzing because we are creating some fuzzy inputs to the program. But for conformance testing is more like because for testing there are three key points. One is how we generate the test case. The other one is how we can feed the test case and execute the target program with our test inputs. And the third one is how do we observe if a bug has happened or not. And conformance testing is more about dealing with the last part, how it is about checking whether the implementation is following some standards or not. So it's more about the last part, but I would say there's fuzzing is very general topic. Talking about the difference between fuzzing and conformance testing is they are emphasizing on different things, I would say. Yeah.
All right. Are there any further questions before we continue on? I'll give you a few seconds if anyone has any. All right. Well, thank you guys so much for your talk. Yeah, if you guys have any questions further for Sheikh and Yukon, please reach out at info@fuzzcon.eu. All right, so
Okay.
thank you so much for your talk.
Okay, thank you.
Bye.
Thank you.
All right, so on to the next one here. So yes, our next speaker is Renee Palage. Little off track there. Actually, so yes, our next speaker is Nico Vincenz. Nico is a cybersecurity expert with ZF. In this role, he is responsible for product cybersecurity analysis and research as part of the Red Team. His talk will take a look at how fuzzing can be beneficial when integrated early and systematically at every stage of the product development process. So if everyone can please give a warm round of applause to Nico.
Yeah, hello, and thank you for the warm welcome, Juliana. And yeah, thanks to everyone today for having me. Yeah, as Juliana said, my name is Nico Vincenz, working currently at ZF Friedrichshafen in the south of Germany in Friedrichshafen. Currently employed as part of the Red Team. Previously was part of the autonomous driving division at ZF, where I'm also was partly responsible for introducing fuzz testing into our cybersecurity process. And yeah, that's exactly also today's topic I want to talk about. So how can we integrate fuzz testing into an automotive cybersecurity test strategy? But before we dig into that, I'd like to establish just some context here. So let's have a very brief recap into the product development process and a cybersecurity test strategy. So basically, every product development process we have is accompanied with a cybersecurity engineering process where we start with a TARA, which is a risk-based approach for defining cybersecurity requirements. And based on those requirements, we derive cybersecurity features which go into our product design. We implement them, integrate them, have a cybersecurity verification validation, and then start production. So far, so good. The cybersecurity test strategy we usually have should include at least those things as functional testing, where we take a look if functionally our cybersecurity specifications are implemented into the project. We do vulnerability scanning, where we say, okay, we have a software bill of materials of our product. Let's look if based on known vulnerability databases, if any vulnerabilities which are known within our product. And we do penetration testing, where we take some human experts, which take manually a look into the product and see if they can exploit anything. And of course, what we want to do now is accomplish this with a fast testing process. So, and how can we do that? I have a very quick rundown how fast testing can be integrated in a cybersecurity test strategy, which is basically first thinking about which kind of activities we need within our development process regarding fuzzing, then defining work products which are necessary for it. Creating a fast test specification, which is tailored for our product, the report, which is the output of it, then having fast testing as a continuous activity, and finally thinking about which kind of other cybersecurity engineering process CP activities are interfaced by our fast testing efforts. So starting with fast testing activities within the development process. Maybe one of the most important takeaways from today is that fast testing is nothing you can just do at the end of your development phase and are done with it. So, for example, we see here the A-Space V model, which is commonly used for development. So it's not just that you would build your product and then after you're done with it, you start testing, but it's really that you continuously from the beginning need to apply fast testing. So even at your software unit stage, you need to do it. And it's also not some kind of a monolith activity, but it's really a split between software and system level fast testing, because as we later see, we have just different needs and just a different structure when we look into the software and the system level. And yeah, for having a process, of course, we need also work products for it. One is the base for it, which is our fast test specification, where we clarify, okay, what do we want to accomplish with our fast testing and how are we going to accomplish it? And of course, the fast test report, which gives us a list of findings, but it's not limited to that, which is also a very important factor of it, is that we have evidence that a sound fast test specification was created by us as well with this report. And yeah, starting with our first work product, the fast test specification. Basically, we have two leading factors for our test specification, which is the fast test scope and our fast test methodology. Both is determined by assigning a test rigor level to assets of our fast test target. And yeah, cybersecurity assurance levels are a helpful tool for doing that. As you can see here plotted, call 0, which will be basically the least rigor, the least assurance we need, until call 4, which is like for highly critical rigor, meaning that we need more test rigor there for assets or interface assigned to that. And of course, an intuitive point of time for doing or assigning those calls, those levels, is during the creation of the Tara, where we have to look into all the interfaces and assets anyway. In an ideal world, of course, we could test everything with highest rigor, which means we would just assign call 4 to everything and test forever and test it really well. But of course, in the real world, it's not possible because we have limited resources, limited time, cannot test forever. So we have to need some way to tailor away things which are not relevant and prioritize our test efforts. And the Tara gives us guidance there, which parts are out of scope. Regarding the fastest methodology, we should, within the specification, already decide which kind of methodology we want to apply to our product and its different cybersecurity assurance levels. And there are multiple characteristics which decide which kind of rigor our fast test has, which is basically the test level we have, the system under test setup, our program structure awareness, the fast test input, and the kind of instrumentation we use. And then we have as output metrics about code coverage, test cases, time, and of course the findings we get from it. Test level, we just saw it earlier. We have different test level on software and system level fuzzing, and with different test levels, of course, we have different kinds of tests we do. So on the software level, of course, we only have source code available. So we can already start really fuzzing single functions, code units or attaching to a program API, whereas on the system level, we would really have already a completely integrated system, which provides us with system interfaces, which we could fuzz, such as, for example, CAN, FlexRay, Ethernet, or also some files which we could supply, such as config files or certificates. Regarding our system under test setup, it's really important which kind of setup we provide for the test. So the initial state and also the transitions we have are play a big role how well the test goes. So for example, some kind of products would need some rest bus simulation to even start up correctly and have a correct initial state without going immediately into an error state. And also for some kind of state transitions, this is necessary. Furthermore, we would, for some kind, also need some credentials. So for example, like a secure access state or something like that, where the fuzzing tool could never reach it without having that credentials provided. The program structure awareness plays a big role. So yeah, the simplest thing we could have is, of course, a black box fuzzing tool, which doesn't know what's going on our test target. I mean, the good thing about that, or the advantage, is that it's very easy to set up. Disadvantage is, yeah, we don't really know what's going on. Opposite of that is would be white box, where we really have all our code available and could symbolically analyze it by a white box fuzzing tool. Has the downside that it's very it's very time consuming and hard to do, often because we have dependencies which we cannot resolve. So we have a middle ground, which would be a gray box approach, where we use instrumentation, which attaches or is linked to source code, or the system which allows us then to trace where our code is executed. We have also different kind of test rigor for the fast test input. There are two approaches. One is having generation-based input, where we would, in the least rigor, just supply some pseudo-random generated input, having a downside that it wouldn't penetrate very far into the system. So if we want to have more test rigor, deeper penetration into the system, we would need some kind of formal grammar or model describing the interface very well. And having at specific points defects or some malicious changes implemented, which will then penetrate or may cause some defects into the test target. The same thing with mutation-based input, where we will have a test corpus, which is built based on valid input data, which is then on certain fields mutated for causing those defects. And finally, I mentioned earlier the instrumentation. There's also different kinds of rigor we have for the applied instrumentation. So the most straightforward one and easiest one to do is just have inbound instrumentation with my test target and look into the answers it provides us, the response messages. The easiest one is just looking if it's alive. A bit more sophisticated would be if we look or try to analyze the kind of message we get there. Regarding external instrumentation, that would be a better kind of or more sophisticated approach, where we really have either a debugger attached already to the test target, or have some kind of agents linked into it, which can exactly tell us what's going on during the test. Yeah, and after we have our methodology going, the fast test done, of course, we get some results back, which we should process into a report. And there's basically following things we get is the code coverage, test case, and time we spent as metrics, which tells of course something about the fast test quality, but they are only conclusive when they are linked to to the test specification. So of course I can see that if I have maybe 30 days of test time and 0% of code coverage, then there's some issue, but I really need the test specification to understand what exactly the metrics mean. Regarding our findings, the most important thing I want to stress here, and that's also the reason I put it at the first place, is that it really should, in the process, it should be clarified who is taking care of the findings. such that we're just not doing testing and nobody ever implements those fixes for the issues we find. The findings itself, they provide, I mean, they are as findings conclusive, but they do not provide lots of evidence sort of regarding, like, if I had really good fuzz test. So if I, for example, don't have any findings, I cannot conclude that I'm done with fuzz testing or that my fuzz test was good. But it's really just conclusive if I also know the test specification and which kind and of test was done there, with which kind of methodology, and whether it was appropriate for the test scenario. After having established those work products, of course, we want to not do it, the tedious task of doing it manually every time, but we want to have it continuously within our process. So we should have a continuous activity here. I just want to sketch one kind of CI workflow, which would be possible to do here. Of course, this is very dependent on which kind of process you decide on the end and what kind of setup you have at your company, or which kind of tooling you have. The workflow I sketch here would be for a software level fuzz test. So a developer, for example, could just write fuzz tests for some kind of software, push it to a version control system repository, the fuzz test branch, which will trigger a pipeline build on an automation server like Jenkins. You would then have it automatically deployed on your test system. The fuzz test would be triggered. A fuzz test server would run those tests, get the feedback, and the result would be reported back to the automation server. And finally, either leading to the pipeline succeeding or failing. And if there were issues found, those should, of course, automatically be tracked in an issue tracking server, where then the developer gets those issues reported so that he can start an investigation what went wrong. And after having all those findings, of course, we want to see how other cybersecurity engineering process activities can now benefit from having such a process established. And taking a look back to our now more complete test strategy, we have following things we can do. We have, of course, based on the fuzz test report, we can, the findings we have use for functional tests to generate negative functional test cases. We can vulnerabilities we might find directly import in our vulnerability database we have, and we can use, if we found some kind of sketchy behavior or some kind of undefined behavior during the test, we can use this for as basis for further investigations during a penetration test. The fuzz test itself can be used also for refining the tower. So if maybe we find that the modeling of the tower or some kind of methodology or some kind of rigor or cybersecurity assurance levels we defined were not correct, and we can refine the tower from that and directly use the new findings to refine our test specification with it. So in summary, the points I would like to stress the most is that it's really important to establish a fuzz test process before the project, such that when a project begins for developing a new product, we can really start activities early and continuously throughout the whole project. The test specification is really important for having a sound fuzz test, so it's really important to take much time for working on that. Responsibilities should be clarified early and for all objectives, and activities should be wherever possible automated, because it's tedious to do them manually. And following all those things, vulnerabilities will just be found earlier during the process, during the tests, and during the whole development, and this goes our remediation costs to be lower in the end. Yeah, and this is already the end of my presentation. So thank you very much for your attention. And if there are any questions, I'm more than happy to answer them. Thank you.
Thank you so much, Nico. Yeah, we have one question so far. Someone asked, do we need to go with functional testing, then vulnerability scanning, then fuzz testing, then pen testing? Can't we go with pen testing directly? Will there be any challenges?
So, yeah, I mean, maybe from the graphic point of view, this is a bit misleading. So you would do it continuously, right? So it's not something you would do in that order, but you won't. I mean, for example, functional testing you would do all the time, right? So if you build something new, if you have a new release, you do your functional tests. Your fuzz testing you do as a continuous activity. Vulnerability scanning you should do also continuously. Only thing which differs is, of course, your penetration tests. I mean, those are very expensive. So in an ideal world, you would also do them all the time. But in the real world, of course, you have some strategic points during a project, maybe 2 or 3 points where you would do a penetration test. So you wouldn't do them all the time. Yeah. So but of course, makes sense to have really good fast testing established before you do your penetration test, such that the penetration tester can focus on things which are left over, so to say. Yeah.
All right. Yes, that was the main question I saw there. So we'll just wait a minute or so if anyone else has any further questions for Nico. Little lag time here usually. I'll give it a minute. All right, if there are no further questions, yeah, if you want to reach out to Nico at all, just message us at info@fuzzcon.eu with any of your further questions or comments, and we will relay that back to you. Thank you so much, Nico, for your talk.
Yeah, thank you for having me. Have a great time. Bye.
Bye. All right, before we move on to our next speakers, I'd like to make a highlight of our conference partner. So I would just like to take a quick moment to thank ISRG and bring you FuzzCon Europe Automotive Edition. The Automotive Security Research Group is a nonprofit, volunteer-driven initiative that promotes the development of security solutions for automotive projects. Their organization represents a collaborative think tank that creates many meaningful insights to be shared with the community and to improve the overall safety of automotives across the industry. This partnership enables us to expand our FuzzCon platform to reach even more innovators and members of the security community. All right, so moving on. Our next speakers, this time for sure, are Renee Palligeri and Rosemary Joshi from Continental. Renee is an expert for automotive software cybersecurity and drives various topics to increase software security across business areas with a focus on software security testing. Rosemary is the head of Global Software Strategy and Innovation and Business Improvement, where she spearheads the software strategy, innovation, and business improvements across all locations, product portfolios, and customers. During their talk, they will share their insights on how they were able to utilize fuzzing to improve overall software quality and how this can be integrated into existing verification and validation processes. So if everyone can give a warm round of applause to our speakers.
Thank you very much. I believe Rosemary also wanted to join. She will actually start the presentation. So let's maybe wait a second or so until she also arrives. Hi, Rosemary.
Hello. I was just trying to change the settings because the connection was slow, but I guess you just finished the introduction because I just rejoined now. So Juliana just finished the introduction, right?
Yes, you can just start.
Okay, so then I can just start. So first of all, thank you, Juliana, for that, Nico, because you set the stage for our introduction into our presentation we're going to show right now, which is beyond cybersecurity. So Juliana, would you be able to? It's not streamed, right? The present streamed yet.
I believe you need to share your screen now. Ah, now I can see it. Okay, perfect.
Just so I'm back again. Let me try if it is working now. Hopefully it works. Okay, so again, sorry for the interruption in between. There was some network issues, but now we are back with the presentation. So thank you for joining us across the globe. So good evening, good afternoon, and good morning to all the participants who joined us across the globe. In the next session, during the next 30 minutes, we will take you through the motivation, how we incorporate fuzzing for improving quality along with security, and then share our experiences of deploying coverage-guided fuzzing. So let me start with some motivation. Now, according to the McKinsey Soft Coster, it shows that the automotive software complexity has grown fourfold in the past decade, whereas the productivity has increased only 0.5 times. Now, looking a bit deeper into what you mean by the complexity, Sheikh already touched upon this point. So we are talking about 150 million lines of code in a car today. And if you take the NASA error rate of 0.5 defect per 1,000 lines of code, which is very low, you're talking about 1,500 errors that is possibly there in the cars today. And let's look a bit more concrete into a Volvo 220 vehicle software. The source code contains 10 million conditional statements and 3 million functions, which are invoked in 30 million places in the source code. So this is going to explode. The complexity will explode in the next decade. And parameter we can gain advantage is to increase the productivity and efficiency. Now, bringing a different dimension about how connected the cars are, we are seeing a shipment of 70 million connected cars by 2026. And we also need to consider that we have increased connectivity interfaces. So we have the Wi-Fi, cellular, Bluetooth, which is common in lots of cars today, but we're also talking about ultra wideband, NFC, and DSRC. And this is resulting in increased attack surfaces. So with this, you well understand the motivation of why we need to focus on quality along with cybersecurity. We see fuzzing beyond cybersecurity. We see fuzzing for quality assurance. Now, let me start with a very simple example. First, we have the specification, and then the developer implements the system based on the specification. Andreas touched upon the topic that even the experts these days cannot develop software that is defect-free, which is very true. And these developers who are experienced, mainly because of the increase in complexity, we see that though they have implemented functionality, which is the intended behavior according to specification, it is also observed that they fail to implement certain functionality or they implement incorrect functionality, which is leading to side effect behavior. Now, the tester finds these bugs during testing using both positive testing and negative testing. Now, the challenge is if the developer is done an implementation a bit different, and because of the vast amount of invalid input for the negative testing, it could be the case that the tester will also fail to detect the defects. And this can be largely covered by fuzzing. And the high level of automation, including defect and vulnerability detection capabilities, makes fuzzing a good choice for effective and efficient testing. Now, let's look into some of the reasons why we have poor quality. So we have no common understanding of requirements, and the clarity reduces from customer, and it gets worse when it reaches the tester. And there is a different level of understanding when the requirements flow from the customer, you break it down, and then when it actually completes the phase of requirement engineering and until we get into the testing, where we are focusing on test-driven development, we are seeing that the understanding of requirements are very different. And the other factor is that we have lesser time for development than before. The complexity is increased, the scope is increasing, and earlier some of our products, we were talking about a project duration of 3 years from the start of development to start of production. And today we see the same products with increased scope and complexity. We have a reduced time of 1 year. And this is going to be difficult going forward because we are going to have more software and we're going to have faster time to market and the need for faster time to market. And we are also talking about software updates in the road. So we will have lesser time for the complex scope we have, and we need to also go for incremental development. We also well seen the fact that we have increased software complexity, and it is also observed that we have low test efficiency and effectiveness. Now, let's see what we can do to improve the quality. Few of you would have already heard about the shift left paradigm. And this ensures that we have an early error detection and prevention because we incorporate testing in an early phase. We can look into how we can increase the test effectiveness because we have a wide space of negative testing, which we saw in the previous slide. And now we need to find effective testing that can cover also the unexpected corner cases. We need to look into how we can increase the test coverage And of course, we all know manual testing is time consuming, so we need to find ways to do test automation and increase the test automation in our systems. Fuzzing can be a game changer, yeah, with the high level of automation and increased test effectiveness and increased code coverage. Therefore, we decided to incorporate fuzzing in process reference models way earlier. So you can see the process reference model, which also includes the cybersecurity engineering process groups. And to start very early stage of software development, we have fuzzing included as a part of software unit verification, software integration test, system integration test, and of course, as a part of the security process for risk treatment, verification, and validation. We will not limit you to the V model here because we are talking about software development, incorporating Agile. And we can also see that this is applicable in the Agile development as well. In the next slides, Renee will explain to you a bit more deeper dive into how we deployed coverage-guided fuzzing and what are the challenges we faced. Over to you, Renee.
Okay, perfect. Thank you very much. Can you see my screen? Yes, this seems to work. Okay, perfect. So let me continue. Now, in this next part, I would like to share some of our lessons learned while trying to apply coverage-guided fuzzing. And I'd like to start with the challenges which we are facing. Now, first off, typically in automotive, we have very large technical diversity when it comes to microcontroller architectures. This is illustrated on the right side. There you can see an overview over the architecture distribution across some of our business units. And this technical diversity typically makes the application of existing tools for fuzzing somewhat challenging because those tools typically focus on x86 and Linux as a platform. This is not something which is as widespread in automotive. And one result of this is that typically you will either need to port your source code. Then this again involves more or less effort. This is pretty much based on your specific project. Or you can choose to use emulation, but this is unfortunately not always that easy or not always an option. Again, it depends on your project. Now, the second issue which we face, this was also mentioned before, are the numerous hardware dependencies. So with coverage-guided fuzzing, as you know, we're testing on a software-only level. So that means we need to abstract those hardware dependencies. But this in effect also means that you need to remodel the hardware behavior with a sufficient precision. And again, this incurs additional overheads. Another challenge are software dependencies. Software development in automotive is typically a very distributed thing. Again, this is depicted in an overview on the right side. This is an AutoSAR Classic implementation, and their components, which are marked in different colors, can all come from different parties. And one result of this is that also tool and build chains are becoming much more complex. And if you want to use coverage-guided fuzzing, in many situations, you want to basically integrate those tools directly into the build chain. You need to do so very early, but this can then become rather challenging. Now, a related challenge here lies in the decision on which level you actually want to start testing, because you have multiple options, as we also will see in the next part then of the presentation. One approach would be to basically focus on single modules, test them in isolation, but this again makes the issue of software dependencies much more prevalent. A complementary approach would be to try to test the overall software system. But now, this typically then means that you also somehow need to take care of the hardware interfaces. And in this case, that means that you, again, have a large additional overhead because you somehow need to simulate or emulate the hardware. And if you should choose simulation, then this means that you need to be able to compile the full software stack in a way that allows you to start with fuzzing. Another typical characteristic of automotive software is the statefulness. So that basically means that individual parts of your overall system typically very much depend on the state of the rest of the system. You typically need to provide a specific sequence of inputs in order to reach specific states. And only if you do so, then you actually can create runtime behavior where a bug might manifest itself, or to just basically get consistent behavior or high coverage. And now reaching those specific states with fuzzing sometimes can prove challenging again and again. You need fine tuning. And finally, this also sometimes makes it harder to just reproduce findings, because it's not always clear if a certain state, which is required to trigger a bug, could also be reached in the real system. And also the fact that you need to stop dependencies and that you need to simulate your hardware makes this more challenging. So usually it's not that feasible to remodel everything with a precision of 100%. Okay. Now, I believe all of those challenges are quite typical when you start testing automotive software. And this being said, what were our experiences when we tried to overcome them? As many projects do, we started our first attempts with coverage gather fuzzing on a unit test level. And now some interesting insights here. So for some tests, most of the bugs which we actually found were within the test code itself, and only a minor part was found in the actual functional code. I believe that should not be too surprising if you think about it, because who tests the test code that much? Yeah. And while, of course, finding then bugs in there also helps to improve the test code, the immediate benefit is rather limited, because this impedes the overall testing progress. The reason behind this is that for many fuzz testing approaches, in order to effectively continue, you typically should directly fix any bugs that you find. Because otherwise, the fuzz testing process will rediscover the same bug again and again. However, if you always directly need also to fix the bugs in the test code, then this will take away time from the resources you have for testing the functional code. The second, and I believe very early and basic insight, is that just introducing sanitizers, such as address sanitizer, for example, really proves to be very helpful. Yeah? So as soon as we did this, we already started finding additional bugs, and we hadn't even started fuzzing yet. We just recompiled our unit test with some sanitizer support. We ran them again, and we found bugs which we had not seen before. So lesson learned here is, because the overhead is not that much, start using sanitizers if you can. Really, it's a quick win. The next interesting points are requirements in terms of coverage. So coverage guided fuzzing here can be really helpful, obviously, because it increases the coverage per definition. Traditionally, often unit tests are used in order to reach a certain level of coverage. But I believe in most cases, unit tests should actually focus on functional aspects, not so much on negative testing. And now in this situation, fuzzing really helped us to rather easily reduce the required effort in order to reach high test coverage. However, of course, it's always important to keep in mind what kind of assurance you get from specific coverage results or types, because yeah, having 100% test coverage really does not mean that you will be bug-free, of course. All right. So now, after those experiences with integrating fuzzing into unit tests, we also started to go more into a direction of module level testing. And here we selected some single high priority modules and started fuzzing them in isolation. So what did we learn here? For some findings, developers soon argued that the generated inputs by the fuzzer could actually never take the same values in the real system. And the data in this case was usually provided by another component, by some dependency, or for example, the RTE. And it was deemed trustworthy because there were well-defined specs regarding potential outputs. And this basically led to the discussion. And I mean, of course, you always can argue in direction of secure coding, defense in depth. But I believe here this is also only half the truth, because we also need to think about well-defined trust boundaries even within our overall software systems, because this in the end will really help you to understand where and what to test in the best way. Yeah? So just going for all public functions of a module might not always make sense, at least not if you have really reliable constraints to the data that will be processed. And another lesson learned was that module dependencies for us can be really tricky. Remember, our goal was to test modules or a number of modules in isolation. And this now implies that we have outgoing dependencies which somehow need to take care of. And for this purpose, we decided to follow a very easy approach, provide fuzz data, not only from the top, so meaning to the dependencies to other modules, but also from the bottom for the hardware dependencies. And basically, the idea was to fuzz the module from all sides. After all, it should be robust and even be able to handle situations where hardware might provide invalid data. We managed to address this by just connecting the fuzzing engines to the stubs and then get the data from them. This, however, also proved to be challenging due to the overhead for stub generation. I guess it's not surprising to learn that doing this manually does not scale at all. After some time, however, we managed to automate this process to a certain degree, which made the approach much more feasible. But still, the generation part needed to be done iteratively again and again because we had regular changes in our inter-module dependencies due to ongoing development. And another lesson learned here was that sometimes we would get findings that just did not make sense. And after additional investigation, we found out actually those were somehow false positives. And this is something that you should not have that much with fuzzing, right? Now, the reason behind this was that basically we just had outdated documentation because the stubs which were generated were based on this documentation. And for some functions, after, for example, the function signature had been changed, the documentation did not correctly reflect this yet. And as a result, the stubs were faulty. And we found stuff that if the function had been called correctly, would not really happen in the real world. However, this, of course, also shows something else. First, fuzzing can even help you find bad documentation. But as a consequence of this, you can also prevent later integration issues. All right. Now, after those experiences with module level testing, we decided to go even a step further and now try fuzzing on a software system level. And this approach definitely has the most overhead. So effectively, what we did was we implemented a simulation, and that simulation now needed to be sufficiently close to the real system to again not produce any false positive findings. This meant additional overhead to fine-tune the system over time so that it works as it should. This could be supported by several actions by, of course, comparing the simulation to the real thing. And what we, for example, did, we took some test cases that described intended behavior and made sure that those test cases also work on the simulated system. But still, to a certain degree, the confidence for any produced findings can sometimes be rather low. And then in this situation, what you might want to do is basically check for, it depends on the nature of the identified bug, if this bug then can also be reproduced against the real system, because basically if you do this on a software system level, the inputs should easily be also reused for the real hardware. However, software system level testing, of course, also has some major advantages. This is why we started doing this. And this is first, we got rid of those inter-module dependency issues. We're testing over a system which is already fully integrated. Second, I believe that was the most important point. Implicitly, we also tested the integration between all modules as well. And now, please recall this point about stub generation and bad documentation. In many situations, bugs, and also specifically security bugs, typically appear at an interface level. So when different parties start integrating stuff, but they have subtly different understandings of how the interfaces are specifically meant. And this is, of course, sometimes hard to test, but in this scenario, then this test is inherently included into the testing process, and as a result, also leads to more meaningful results. So far, this has been the approach which we have chosen and right now are also using on several projects. Now, regarding those overheads, of course, for all new projects, we typically still have those additional onboarding efforts to get everything up and running and for the fine tuning. But what we noticed is over time and with platform reuse, this overhead really becomes much more manageable. And of course, at the same time, you also always need to prioritize a bit to get the most out of your efforts. Okay, so let's summarize. Based on our experiences, fuzzing, specifically coverage-guided fuzzing as well, has huge potential even beyond cybersecurity. If you use it early enough, you might not even need to check for a specific bug if it has security implications or not. You just fix it and then you're good. At the same time, we have learned that specifically for automotive software, it can be really hard to apply, and that definitely does not exist one size fits all approach yet, unfortunately. But if you manage to overcome those challenges, this is a really nice approach. And the interesting thing is that over time, with refinement and automation, it also becomes more and more effective. Now, when you think about fuzzing as a testing technique, I think it's quite clear that it is an immensely valuable addition to other techniques which exist as well. But at the same time, it does not really stand for itself. And what we need is we need to think about how to integrate fuzzing with those other testing techniques, because some of those are here to stay. They cannot just be replaced. And in the end, you want to have a holistic approach that basically helps you create the best results for a given amount of effort that you can invest. And of course, this is not just about the technical integration, but it's also about integration into verification and validation processes. Yeah, because I believe this is basically just the essential part in order to get everything together then. All right. Thank you very much. And I hope we still have time for some questions.
Yes, thank you so much. Here, I'll just toggle that off. There we go. I see we just have one question so far. David wanted to know if code coverage is really the metric that one should strive for.
Maybe I can start with. So first of all, David, thank you for the question. It's an interesting question because there is often debate between developers. So some developers says, this is a dumb metric to evaluate the code quality. But there are also developers who claim to be proud that, yes, my code is 100%, having 100% test coverage and the highest quality. And the truth is somewhere in between. So we need to now find efficient ways that we can actually leverage fuzzing to increase code coverage. So as a part of fuzzing, we can, and Rene already touched upon, coverage guided fuzzing. And this is where we need to find what's the right balance between how we can attain code coverage efficiently. So it is still, so to give you the final answer, it is still a valid parameter for code quality and not to be ignored, especially when we are moving in the direction of test-driven development.
Thank you. Another question we have from Jaya Soda there is, why is fuzzing hard to apply on automotive software?
Okay, I guess I can take this one. So I tried to address this a little bit in the first part of my section in the talk, where I was talking about those specific challenges. The thing is that automotive software is not like the typical software which you see in the IT domain. We are very strongly in the embedded context here, but existing tools for fuzzing, and again, I'm speaking mostly about coverage-guided fuzzing, so on a software level here, they have evolved a little bit more in the domain of x86 Linux, where this is now also a little bit easier to apply. But as soon as you go into automotive, you have those specific challenges. You have hardware dependencies, more software dependencies. You have architectures that you typically not encounter outside of automotive, and where the existing tools not always necessarily work out of the box. You have the statefulness problem, and again, some other issues. And altogether, this makes it more challenging. But again, the lesson learned for us is you can overcome those challenges. And if you do, really still you have a lot of added value, and over time it becomes more efficient.
All right, thank you so much. If there are no more questions from our community, and I think there are no more, I want to thank you so much for your talk. If anyone else has any more questions, info@fuzzcon.eu, we'll get them over to Renee and Rosemary for you, and we'll get those questions answered. So thank you so much for your talk.
Thank you.
Thank you. All right. So we are in the final stretch. So our final speaker is Victor Marginian from Argus Cybersecurity. Victor is the pre-sales worldwide director at Argus Cybersecurity Ltd. He is passionate about the combination of automated driving, machine learning, and the impact on cybersecurity. This is actually his second FuzzCon Europe Automotive Edition with us. Last year, he gave a really great talk on the topic of fuzzing and machine learning, which you can check out on our website at fuzzcon.eu. His talk this year will highlight the importance of end-to-end security verification, including fuzzing on software and real interfaces. Please give a final welcome to Victor.
Hi, Juliana. Hope everything works well with the connection. So I will start with the presentation now. Let me just share my screen, and we start with that. Good. So basically, my talk will be about how we can improve the automotive business by shifting right and integrating basically the BSOC together with the development part. We've done this talk together with Michal Frankel, our Argus VP product. Unfortunately, she couldn't join. She apologizes, but she had an emergency, medical emergency. So I will do it alone. Basically, I will start by speaking a bit about Argus, who we are, and why we are in the market. So we currently have more than 65 million vehicles that will be secured with Argus technology starting 2021 across 35 production projects and with 16 different manufacturers. We have roughly 200 employees with offices across the globe in Korea, Japan, Germany, France, and US. We invested so far more than 1,000 man-years in Argus technologies and research, and we have more than 70 granted and pending automotive cybersecurity patents. Our goal is to reduce the cybersecurity cost and complexity by providing reusable software and direct OEM engagement. We have seamless integration across the product portfolio for different ECUs. And we have automotive grade ASIL-B ready, and we are developing in alignment with the ASPICE Level 2 requirements. We, of course, have also partnerships with leading industry players like NXP, Marvell on the in-vehicle side, and with Microsoft and Amazon on the cloud side. I will start by explaining a bit the automotive mega trends, and all of them need to consider cyber implications, trying to give a bit of an overview of what is currently happening in the automotive business. So we clearly see the autonomous driving as a mega trend, and the implications are that they bring with them the complex and safety relevant software and high performance computers. So this means that 64% of the customers would switch OEMs for a better autonomous driving capabilities. And of course, we know, and as I also discussed last year, that the autonomous driving comes with huge implications and the combination of safety and security, because you cannot have safety products without having a secure product, especially when the car is on the road. Then another mega trend is related to connectivity, and it's clear that you need to have performant in-vehicle networks. So now that's why we see the shift to Ethernet, over-the-air updates to be able to react to potential software issues, to activate new features, and to fix potential vulnerabilities. And with this comes also the cybersecurity implication. And we know already from this study that 95% of new vehicles sold in 2030 will be connected. The trend is the electrification, and this clearly adds a new electrical package that, of course, might be at risk if someone really wants to hack into the car. It has new powertrain applications, and from what we learn with this mega trend is that 53% of the new vehicles sold in Europe could be electrical vehicles, and this includes, of course, the plug-in hybrid, the fuel cell EVs, and so on. Another mega trend is about shared mobility, and this for sure is requesting for features for individualization, and this comes together again with security implications, bringing risks for for the personal data, and with keyless entry, which again brings another risk of being able to completely hack a fleet that is shared. And basically, 2 out of 3 of the US customers expect their shared mobility usage will increase over the next 2 years. And we can see this with the big cities across the world, where we see everywhere all the scooters, all the cars that can be used without any problems. And you can unlock them with the phone. All these cars are still based on old architectures that, of course, share the risks of cybersecurity. Now, what I will speak and where I will focus today in this presentation is more about the disconnect that we currently see between the tier ones and the car manufacturers and the IT operational teams. We will try to propose a framework for integrating the two worlds, the IT and the automotive world. And I will also detail the integration proposal for enabling collaboration between the development and the operational teams. And I will start with the status quo, with the typical security organization that currently, let's assume that they are doing their best, and they are already performing penetration testing. On the other side, on the IT side, they already have a vehicle security operation center. So basically, most OEMs and tier ones are currently performing penetration testing for vehicles and connected ECUs. From what we see, fuzzing is mostly done at the interface and black box level. We see clearly a trend of trying to add software fuzzing, like the one that Code Intelligence is providing. But currently, most of the OEMs are focusing on the interface and black box level. Then vulnerabilities that are discovered as part of the private penetration testings are currently, from what we see in the industry, not integrated with the VSOC solutions. And they mainly help the development teams for fixing the products before the start of production of the vehicle. Then on the other side, on the IT side, the vehicle security operations centers, we see that the majority of OEMs are preparing to have the vehicle security operations, but full continuous integration, continuous development up to the VSOC integration is still not planned. And this is clearly a pillar that could be better used. But this is currently the status quo. The vehicle vulnerability management solutions like the digital twin or ECU software and hardware replica, however you would like to call it, they are in general not planned to be integrated by the OEMs inside the VSOC. We've seen different cases, but in most of them, we see also here a disconnect, and we see that also this part of the checking is mostly focusing on the development side and not to the operation side. So now I think everybody that is working in automotive is aware of the V model and the solutions for the secure products. But here I would like a bit to go into the details of what are the different tools that can be applied. And this would already be an organization that is doing all what is needed for ensuring a secure product. So if you start from the left, from the upper side with the requirements analysis, you can have cybersecurity and architecture design planning to achieve that. Then you need to do the system design, and for that you need to perform a threat analysis and risk assessment. It can be done by using a tool. This can be done by manual work. Then you need to have the architecture design to make sure that all the product is secured. Then you can do the component design. And here already, if you want to introduce security in the products, you need to have the intrusion detection protection systems, and you can already define the rule set and to have the configurations. And then when it comes to the implementation side, it's clear that already at this stage, you need to have a software fuzzing that is integrated in the CI/CD, communicating with GitHub, having it run on the nightly builds, having it run at least on the hardware builds, on the weekly builds. The next part is about the component testing, and here is the part where ideally you will have a fuzzing tool for the real hardware, and here ideally you can use software fuzzing results to validate them as part of the component testing, by validating whatever is discovered as part of the software checking, by checking if they really happen on the testing bench. Then, of course, the next step is the integration testing, where you can add on top the penetration testing, and that will allow you to see the whole system, how it's behaving, and to double check again if the fuzzing, if the findings from the fuzzing or from the component testing are being confirmed. The last step would be the system test, where you can also validate the network validation. You can perform the network validation, and you can do this at, for example, at the vehicle level. And the last step would be the acceptance test, where the manufacturer can really check that whatever that you claim that you can provide is really performed and in a secure way. And here you have the connections with the operations, where currently there are several solutions that can be implemented, like vulnerability management, like fleet protection, and of course everything needs to be enhanced and enriched with the threat intelligence by checking what are the vulnerabilities that are really exploited out there, and that will allow a good focus on fixing them. So this is that would say would be the ideal situation for fulfilling the V model and having a secure product. And still, this is not currently enough, because the part of the vulnerability that are coming from the CI/CD are not automatically integrated. And basically, this is coming purely from organization causes. And it's just because there are different teams that are doing this. So basically, what we see as generating drawbacks is, if you keep the CI and CD and the VSOC separate, you will for sure slow down the process of CVE reporting that might be found with the fuzzing. This will leave the VSOC teams blind against zero-day vulnerabilities that would otherwise could pop up directly from the CI/CD in the first in the vehicle vulnerability management, and the ones that are really confirmed in the VSOC. This is also not allowing to test attacks that are detected on the fleets using the CI/CD environment, because whatever is discovered on the real fleet takes a lot of time before they arrive back to the CI/CD for being confirmed. This also doesn't allow a fast enough update for the IDPS rule set, because findings can be easily used to update the rule set and improve the overall protection. So currently, because of the different processes that are in the supply chain, it would probably take from weeks to months to update such a rule set, because of how long this process is taking. And this is also not allowing to fully use the threat intelligence capabilities, also as part of the CI/CD, because even if you see that some vulnerabilities are exploited in the wild, this only stay as part of the VSOC operation, as part of the vehicle vulnerability management, but they are not fed back to the software so that they can be easily updated and fixed. So basically, what we are proposing as solutions, we think that integrating the current solutions and making them communicate using the CI/CD just as a different data source for the VSOC could solve such a problem. then the feedback of the alerts that are discovered with the VSOP to the CI/CD environment will allow product improvements in the mostly automated way. And the use of the threat intelligence to allow prioritization for both VSOP teams that are mitigating the threats and the R&D teams that are updating the IDPS products. Now, explaining a bit how this would work, we will start from the top now, so not as you would typically use the V model. So just imagine that the vulnerability management and the fleet protection here are communicating between them. So you would feed the public CVEs and the threat intelligence to the vulnerability management. You would feed whatever data you are collecting from the fleet protection and also do the vulnerability management. You need to have, of course, a process permission manager that is allowing this. And then you are, again, capable of doing the same. Whatever you find, you can check them again as part of the system test. You can use the automated tools for network validation to verify them. If they are being discovered, or if you need additional investigations, they can be moved to the integration test for doing penetration testing or validating whatever you checked as part of the penetration testing. They can go even more to the component test. And here already they can be automated and really checked. So all the tests that are being done typically using fuzzing tools or using the software fuzzing integrated in the CI/CD, they can you can purely update the test that you are performing then immediately, and you can really check in real time the implementation and correct it. So this can be done in two different ways, either by just modifying the software, so updating basically if there are software bugs, they are just being updated, or if, for example, the software is coming from a third-party provider that is not able to fix it, using that also the intrusion detection rule set configuration that is then deployed in the vehicle can be updated, and again everything can follow the same process to get there. So that's clearly an improvement, and this for sure will be enhanced by the communication between the software fuzzing that is integrated in the CI/CD, the fuzzing tool that can validate this on the actual hardware, and then pushed back along the supply chain to the fleets. And this allows then to have vulnerability detected in CI/CD with fuzzing immediately checked and highlighted for the fleet protection. The attacks from the fleet protection can be validating using the CI/CD environment, and then the IDPS rule set can be updated. And of course, the threat intelligence ensures the right prioritization, because sometimes it can happen that there are just too many vulnerabilities for some libraries that are being used. But then the threat intelligence can help in this direction by pointing to the ones that are really exploited in the wild and allowing the tier ones and the OEMs to do the right prioritization. So this is in general the proposal. The next slide is showing a bit about how this data can really be used. And I know it's a full slide, but it's typically because it adds several pillars for threat monitoring and reaction. And here we will need to start from the top, focusing on the assets and the asset sources. So basically in vehicle, you have all the TCUs, all the ECUs, Ethernet and CAN that are collecting the logs. Typically for that, we need the DBC of the CAN, the AirXML for the Ethernet, SBOM extracts to know exactly the software versions that are inside. And then external with mobile apps, with mobility services, and here you can integrate the logs, the files, and the API. And just imagine that all what is coming here is coming together with checked vulnerabilities with CVEs that are updated in real time to all the different dashboards. And then you have different pillars for data sources that are being checked, that are being analyzed, that are being then presented as dashboards. And let's take the several examples. So telematics, you have the data source of telematics, you can filter them, you can analyze them, you can do events correlations. And with telematics, imagine that you can discover all the different vehicles that have their, I don't know, some features that are being activated without having the right. This can be discovered, and you can then detect the fraud, and you can publish it in the dashboard. In the upper part, with the playbooks and best practices that such a product can provide, you can have the mitigation and remediation. So basically detecting such a fraud and highlighting it as part of the OEM fleet management. The second part is about vulnerabilities. So what I was just explaining before, with vulnerabilities that are monitored from different sources. So either CI/CD, either private vulnerabilities that are being discovered as penetration testing, or from the CVs that are published. All of this can be then analyzed and perform a trend analysis from them. Of course, they can be presented as part of the dashboards with alerts, with reports. And then, of course, you can add to that playbooks. And I think the easiest example is that you can then identify what libraries or what software has a vulnerability, and then you can push a software update to just fix it. Another one is about threat intelligence data that can again be aggregated, and you can detect using that different anomalies, and you can again present them and implement playbooks using best practices. All these 2 points, the vulnerabilities and threat intelligence data, can be integrated, and they are for sure enhanced if you are feeding them with CI/CD data. The last one is basically real-time events from the onboard, so basically coming from the vehicles. So whatever you can discover with the intrusion detection system from the TCUs, from the ECUs, from all the different vehicles, can be immediately shown as part of the dashboards that can be provided. They can be clustered, and they can be then identified if certain areas of the fleet, all the vehicles that are in a certain area can be attacked. And then again, you can react by pushing again configuration updates to limit the impact on the fleet. So this is basically what the threat monitoring and reaction can achieve, and where, of course, enhancing with different data from telematics, from vulnerabilities that are being collected from different sources, performing the prioritization based on the threat intelligence data, and then correlating it with the real-time events from the onboard can be of use for protecting the fleet. So I think that's all my talk for today. So Juliana, please let me know if there are any questions.
Yes, thank you so much, Victor. Don't see any questions in the chat yet. Are there any questions anyone has for Victor about his talk? I'll just give it a second. All right, seems like we don't have any questions. Everyone's at the end, so thank you so much, Victor, for your talk. Again, everyone, if you'd like to reach out to Victor, just pop a message at info@fuzzcon.eu, and any questions you have, we'll get them back to you. So thank you so much, Victor.
Thank you, Juliana.
All right, so yes, that brings us to the end of FuzzCon Europe Automotive Edition. I'd like to thank everyone for your participation this year, and also a very big thank you to our speakers from the entire FuzzCon team. We hope you all learned a great deal from the truly insightful talks given by our speakers this year. If you'd like to have a look back at any of these talks, all the recordings will be up on the site by next week at fuzzcon.eu. We'd also love to hear from you all. So if you could send a message at, of course, again, info@fuzzcon.eu with any questions or feedback you might have, or topics that you would like to see us cover at next year's conference, we'd really appreciate them. If you want to get your hands on some easy-to-use fuzzing tools yourself, please check out our website at fuzz.ci. It's open source and currently supports Java and C++ with further languages on the roadmap. So thank you all again so much for coming. We hope to see you at the next FuzzCon.